Section 4.3 Redundancy of Prefix Codes. In Section 4.1, we have proved the entropy bound for a DRE uniquely decodable code. That is, the expected length of such a code is at least equal to the DRE entropy of the source random variable x. In this section, we revisit the entropy bound by presenting an alternative proof specifically for prefix code, which offers much insight into the redundancy of such codes. Let x be a source random variable with probability distribution p1, p2 up to pm, where m is greater than or equal to 2. A DRE prefix code for x can be represented by a DRE code tree with m leaves, where each leaf corresponds to a code word. Denotes the leaf corresponding to probability pi by ci and the order of ci by li. Let the alphabet be 0, 1 up to d-1. Let script I be the index set of all internal nodes, including the root, in the code tree. An internal node of a code tree is a node that has at least one descendant. To decode a code word of a prefix code, we can trace the path specified by the code word from the root of the code tree until it terminates at the leaf corresponding to that code word. Let CUHK be the probability of reaching an internal node k during the decoding process. The probability CUHK is called the reaching probability of internal node k. Evidently, this probability is equal to the sum of the probabilities of all the leaves descending from node k. Here is an illustration of the reaching probability CUHK of an internal node k when d is equal to 3. Clearly, CUHK is equal to the sum of all the probabilities of the code word descending from node k, which are marked in red. Let p tilde k comma j be the probability that the jth branch of node k is taken during the decoding process. The probabilities p tilde k comma j, where j is between 0 and d-1, are called the branching probabilities of node k, and CUHK is equal to summation j p tilde k comma j. Once node k is reached during the decoding process, the conditional branching distribution is obtained by normalizing p tilde k comma j. That is, the distribution p tilde k comma 0 divided by CUHK, p tilde k comma 1 divided by CUHK, all the way to p tilde k comma d-1 divided by CUHK. Then define the conditional entropy of node k by h sub k equal to the DRE entropy of the conditional branching probability. Note that this conditional entropy of node k is upper bounded by log of d in the base d, that is 1. Here is an illustration of the conditional branching distribution of internal node k when d is equal to 3. Lemma 4.19 says that the source entropy hd of x can be expressed as a sum in terms of the code tree. Specifically, this is the summation of CUHK times hk for all internal node k, where CUHK is the reaching probability of internal node k, and hk is the conditional entropy of internal node k. We now prove lemma 4.19. We will prove the lemma by induction on the number of internal nodes of the code tree. For the base case, if there is only one internal node, it must be the root of the tree. Then the lemma is trivially true upon observing that the reaching probability of the root is equal to 1. We now give the details of this argument. Recall that the source distribution is given by P1, P2 up to Pm. Observe that M is less than or equal to D, otherwise the code tree must have at least 2 internal nodes. Then all the code words have length equal to 1. This is illustrated in the figure without loss of generality. Note that there are some unused branches at the root if M is strictly less than D. Since the reaching probability of the root is equal to 1, it is easy to see that the conditional branching distribution of the root is given by P1, P2 up to Pm, and some zero probability masses in case M is strictly less than D. Then H root, the conditional entropy of the root, is equal to the theory entropy of this conditional branching distribution, which in fact is equal to the entropy of the source variable x. It follows that summation CUHK HK over all internal node k is equal to Q root times H root because there is only one internal node, namely the root, where Q root is equal to 1 and H root is equal to the entropy of the source variable x. This verifies the lemma when there is only one internal node in the code tree. Now assume that the lemma is true for all code trees with n internal nodes, and consider a code tree with n plus 1 internal nodes. This is illustrated in the figure. Let K be an internal node such that K is the parent of a leaf C with maximum order. Each sibling of C may or may not be a leaf. If it is not a leaf, then it cannot be the ascendant of another leaf because we assume that C is a leaf with maximum order. Now consider revealing the outcome of X in 2 steps. In the first step, if the outcome of X is not a leaf descending from node K, we identify the outcome exactly. Otherwise, we identify the outcome to be a child of node K. We call this random variable V. This is illustrated in the figure. For the case that we identify the outcome of X to be a child of node K, we can simply regard random variable V as being equal to node K. If we do not identify the outcome exactly in the first step, which happens with probability QK, the reaching probability of node K, we further identify in the second step which of the children of node K the outcome is. We call this random variable W. If the second step is not necessary, we simply assume that W takes a constant value with probability 1. Then X is equal to the pair of random variables V and W. Now observe that the outcome of V can be represented by a code tree with n internal nodes, which is obtained by pruning the original code tree at node K. This is illustrated in the figure. Since the code tree representing V has n internal nodes, by the induction hypothesis, the entropy of V is equal to summation QK prime HK prime, where K prime is an internal node not equal to K. That is, the summation is over all internal nodes of the code tree representing V. Then we have Hx is equal to H of V comma W, which by the chain rule is equal to entropy of V plus entropy of W given V. Now the entropy of V by the induction hypothesis is given by this summation. For the entropy of W given V, we consider 2 cases. For the first case, the random variable V is not equal to node K, which happens with probability 1 minus QK. The conditional entropy is equal to 0. For the second case, the random variable v is equal to node k, which happens with probability QK. For this case, the conditional entropy is equal to HK, the conditional entropy of node K. Now this term goes away, and the term QKHK can be combined with the summation with K prime equals K. And so, we have summation QK prime HK prime for all internal node K prime of the original code tree. Therefore, the entropy of the source random variable is equal to summation QK prime HK prime for all internal node K prime. This completes the proof of the lemma. Lemma 4.20 says that the expected length of a prefix code, L, can be expressed as summation QK for all internal node K of the code tree. Before we prove this lemma, we first illustrate the proof of this lemma by means of an example. Consider this prefix code with 6 code words, which are assigned the probabilities P1, P2 up to P6. The expected length of this code is equal to 3 times P1 plus 3 times P2 plus 3 times P3 plus 3 times P4 plus 2 times P5 plus 2 times P6. Let us now focus on the code word that is assigned the probability P1 and trace from this code word back to the root. Along the way, we encounter 3 internal nodes, where the number of internal nodes encountered is exactly equal to the length of the code word. Now we put a copy of P1 at each of these internal nodes. Note that the sum of these 3 copies of P1 is exactly equal to the contribution of P1 in the expected length of the code. We do the same for the code word assigned the probability P2, for the code word assigned the probability P3, for the code word assigned the probability P4, the code word assigned the probability P5, and the code word assigned the probability P6. Let us now start from the code word assigned the probability P1 and trace all the way back to the roots. Along the way, we find 3 internal nodes. Note that the number of internal nodes on this path is exactly equal to the length of the code word, that is 3. Then we put a copy of probability P1 at each of these internal nodes. Notice that the sum of these 3 copies of P1, that is 3 times P1, is precisely the contribution of P1 in the expected length of the prefix code. Then we do the same for P2, for P3, for P4, for P5, and P6. It is then clear that the total value of all the probability masses that we have put at the internal nodes is equal to the expected length of the code. Moreover, the total value of the probability masses that we have put at an internal node is equal to the reaching probability of that internal node. For example, the sum of these 6 probabilities, which is equal to 1, is precisely the reaching probability of the root. And the sum of these 4 probability masses is equal to the reaching probability of this internal node, so on and so forth. Therefore, the expected length of this prefix code is equal to the sum of all the reaching probabilities of the internal nodes, and this verifies lemma 4.20. We now give a formal proof of lemma 4.20. First, we define A sub ki to be equal to 1 if leaf ci is a descendant of internal node k, as illustrated. If leaf ci is not a descendant of internal node k, we set aki to 0. Then li, the length of the ith coword, is equal to summation aki for all internal node k. Because there are exactly li internal nodes of which ci is a descendant, if the order of ci is equal to li. And the summation on the right-hand side simply counts the total number of such nodes. On the other hand, QK, the reaching probability of internal node k, is equal to summation aki times pi over all I, where this summation is precisely the total value of the probability masses descending from internal node k. Now the expected length of the code L is equal to summation I pi times Li, where Li is equal to summation aki over all internal node k. In the next step, we change the order of the two summations. Here, summation I pi times aki is equal to qk, the reaching probability of internal node k. Therefore, we have shown that L is equal to summation qk for all internal node k, proving the lemma. We are now ready to introduce the notion of local redundancy. Define the local redundancy of an internal node k by Rk equals Qk times 1 minus Hk, where Qk is the reaching probability of internal node k, and Hk is the conditional entropy of internal node k. This quantity is local to node k in the sense that it depends only on the branching probabilities of node k. Specifically, if the branching probabilities of node k are known, then both Qk and Hk are determined, and hence Rk is also determined. In the definition of Rk, since Qk is strictly positive, Rk is equal to 0 if and only if Hk is equal to 1. That is, the conditional branching distribution of node k is the uniform distribution over all the d branches at node k. In other words, p tilde kj is equal to qk divided by d for all j between 0 and d minus 1. When this happens, we say that the internal node k is balanced. This is illustrated in the figure for d equals 3. Also note that the local redundancy Rk is always non-negative because Hk is upper bounded by 1. The next theorem, called the local redundancy theorem, says that the redundancy of a DRE prefix code can be written as the summation of the local redundancies at all the internal nodes. We now prove the theorem. Consider R equals L the expected length of the prefix code minus the theory entropy of the source random variable x. Now L is equal to summation CUHK for all internal node k, and HD of x is equal to summation CUHK times HK for all internal node k. Combining the two summations, we have summation k, QK times 1 minus HK, which is equal to RK, the local redundancy at internal node k, by definition. This proves the theorem. The next corollary can be regarded as the entropy bound for prefix code. It says that the redundancy of a prefix code is always non-negative, with equality if and only if all the internal nodes in the code tree are balanced. The proof goes as follows. Consider R, the redundancy of the prefix code, equals summation RK for all internal node k. Since all local redundancies RK are non-negative, R is also non-negative. In particular, R is equal to 0, that is, the entropy bound is tight, if and only if RK is equal to 0 for all internal node k, which means that all the internal nodes in the code tree are balanced. This proves the corollary. Here are a couple of remarks. First, the entropy bound says that for a theory uniquely decodable code, the theory entropy of the source is at most equal to the expected length of the code. This makes sense because intuitively, each theory symbol can carry at most one bit of information. Therefore, when the entropy bound is tight, each code symbol has to carry exactly one bit of information. In the context of a prefix code, the interpretation is as follows. Consider revealing a random code word one symbol after another. Corollary 4.22 states that in order for the entropy bound to be tight, all the internal nodes in the code tree must be balanced. This means that as long as the code word is not completed, the next code symbol to be revealed always carries one bit of information because it is distributed uniformly on the alphabet. We now present a technique to obtain a lower bound on the redundancy of a prefix code. Consider writing R as a summation of RK for all k in I, the set of all internal nodes. If we replace I by any subset I prime, the summation can only decrease. If we can compute the local redundancies RK for all k in I prime, then we can compute the lower bound, summation RK, k in I prime, on the redundancy of the prefix code. Example 4.23 is an illustration of this method. In the binary Huffman procedure, the two smallest probabilities, PM-1 and PM, are merged to form an internal node of the code tree. Evidently, the reaching probability of this internal node is PM-1 plus PM, which is illustrated in the following figure. The conditional entropy of this internal node is the binary entropy of the conditional branching distribution of that node. Accordingly, the local redundancy of this internal node is equal to PM-1 plus PM, that is the reaching probability of this internal node, times 1 minus the conditional entropy of this internal node. Then this expression forms a lower bound on the redundancy of the prefix code. Note that this lower bound on R depends on the two smallest probability masses in the source distribution. In general, if we have more information about the source distribution, then we can obtain better bounds on the redundancy of a prefix code for that information source.